Hello, dear students of second MSc Chemistry. In the previous class, we saw what is the necessity for chemical shift. Once again, let us recall, since the NMR spectrum is recorded by two different methods, that is field speed method and pulse method, the data regarding NMR spectroscopy becomes voluminous and it is not uniform. So, to maintain a uniformity in the data for a chemical compound that is recorded by any one of these methods, a universal unit, a derived unit, namely chemical shift, was introduced. We have seen what is meant by chemical shift in the last class. So, first, to derive the unit, namely chemical shift, we are recording the NMR spectrum with a reference compound. Tetramethylsilane is the reference compound. With reference to the 12 protons of tetramethylsilane, the experimental compound and its chemical shift values are compared by the NMR spectrometer itself with the help of a microprocessor. So it is converted into a common unit called as chemical shift, which is a derived unit. We saw the reasons for choosing tetramethylsilane in the examination or in the viva voce, or if you sit for any interview in a private company, you may face a question regarding the reference compound in the NMR spectroscopy. You must know what are the reasons for choosing tetramethylsilane as the reference compound in NMR spectroscopy. I have given 4 reasons. So please remember the 4 reasons. So we have seen what is meant by chemical shift. Chemical shift is indicated by the symbol delta value. Delta. So that is nothing but the shift from the standard TMS tetramethylsilane divided by oscillator frequency into 10 to the power 6. Okay. The difference between the signals of tetramethylsilane and the protons of compounds. So new sample minus new TMS divided by oscillator frequency into 10 to the power 6. Frequency of tetramethylsilane protons is assumed as 0. So frequency of the protons in the sample, different protons, that will give you the chemical shift values for the different protons in the compound. And I have explained the necessity for multiplying it by 10 to the power 6. So we will get the delta value in whole number. Since it is multiplied by 10 to the power 6, 10 to the power 6 is equal to 1 million. So it is called as parts per million. The unit is called as parts per million. That is a unit for chemical shift. Now, I made a comparison to understand the difference between, to understand the uniformity of chemical shift. Whether it is recorded in a 60 MHz instrument or 100 MHz instrument, the chemical shift value is the same, delta value. It is a derived unit. But in a 60 MHz instrument, 1 parts per million is equal to 60 Hz. Whereas in a 100 MHz instrument, 1 parts per million is equal to 100 Hz. That difference we realized with this example. So it is a universal unit. I have proved that chemical shift value is a universal unit. Now in this class, let us focus on the factors influencing the chemical shift value. See, just now we have discussed the chemical shift value is a derived unit. How the unit is derived? The unit is derived from the frequency of absorption of various nuclei with reference to the compound, namely tetramethylsilane. So there are various factors which are influencing the chemical shift value, the frequency of absorption, ultimately the chemical shift values. See, already we have seen when you are applying the magnetic field H0, the proton is not experiencing the magnetic field H0 because the proton is surrounded by the hydrogen atom in the organic molecule or the hydrogen nuclei in the organic molecule. It is surrounded by electron density. It is surrounded by electrons. A carbon, hydrogen, sigma bond is there. The sigma bond is made out of 2 electrons. So, the electrons are revolving around the hydrogen nuclei to neutralize the charge of the protons. They are involved in the bonding also. As a result, the magnetic field applied, that is H0, is not fully felt by the proton. So because of this, we say that there is a parameter called shielding parameter. It differs from nuclei to nuclei. As a result, the magnetic field experienced by the nuclei is given by H0 into 1 minus sigma, where sigma is the shielding parameter. So, you have clearly understood what is meant by shielding. Shielding means the external magnetic field is shielded so that the nuclei cannot experience the magnetic field fully. So, this is called as the shielding effect. See, just opposite to shielding, we have deshielding also. In shielding effect, the magnetic field experienced by the nuclei is less than the applied magnetic field, and there are a few instances where the applied magnetic field is experienced higher by the nuclei. There are some situations also. That means the protons are not shielded, they are deshielded, just opposite of shielded. H0 is the applied magnetic field. If the proton experiences a lesser magnetic field than H0, then we can say shielding effect is operating. If the proton experiences a magnetic field which is higher than the applied magnetic field H0, then you can say deshielding effect is operating in that nuclei or proton. So, this is called as shielding and deshielding effect. It is an important factor that is influencing the chemical sieve. So we should see or we should discuss how the shielding and deshielding of a nuclei occurs in organic molecule. First important factor is the electronegativity of substituents present in the organic molecule. An organic molecule, being a carbon compound, may have hydrogens. It may have heteroatoms like oxygen, nitrogen, sulfur. In addition to this, it may have substituents like halogens in the form of nitrogen in the form of amino groups, oxygen in the form of OH groups, carbonyl groups. So all these things are possibility. Silicon is also possible. We have seen one example, tetramethylsilicate, where one silicon atom is substituted with 4 methyl groups. Just like carbon, silicon is also from the same family, so it has shows a valency of 4. So 4 is the valency of silicon, so 4 methyl groups are substituted. Or we can say silicon is substituted over each methyl group in tetramethylsilicate. But the silicon is highly electropositive when compared with carbons. So the electronegativity and the electropositivity of a substituent must be considered when you are discussing about the shielding and deshielding effect that is operating in a organic molecule and its influence over the chemical shift value. First, let us see how the electronegativity of the substituent affects the chemical shift value. For this, I have a tabular column. See, in the tabular column, we have the compound and we have the chemical shift value delta. So first compound is your tetramethylsilane. Silicon is electropositive. Anyhow, since we are deriving the chemical shift value in relation with the or in position with the chemical shift frequency of absorption of the 12 protons in tetramethylsilane, it is assumed as 0. But when one of the hydrogen is replaced by methane, CH4 is the formula. If one of the hydrogen is replaced by iodine, iodine is an electronegative element. It is from the halogen family. The halogen family first member is fluorine, chlorine, bromine, iodine. And last one is astatine. Astatine being a metal, we need not worry about it now. So in the halogen family, we have fluorine, chlorine, bromine, iodine. The electronegativity decreases on descending a period. If you move from fluorine to iodine, the electronegativity decreases. Anyhow, iodine is also having electronegative character, being a member of the halogen family. But the electronegativity is maximum with fluorine, and fluorine is the most electronegative element in the periodic table. So when you put an iodine atom in the place of a hydrogen, the electronegativity of iodine influences the chemical shift value. So the protons of methyl iodide appear at 2.16 parts per million. When the iodine is replaced by bromine, the value is 2.65. When the bromine is replaced by chlorine, methyl chloride, the delta value, chemical shift value is 3.10. And if the chlorine is replaced by fluorine, then the chemical shift value is very high. It is 4.26 among the members of the halogen family. So from this table, it is very clear that the chemical shift value increases with the electronegativity of the substituent. The electronegativity of the substituent increases from iodine to fluorine. It decreases from fluorine to iodine. Since the electronegativity increases from iodine to fluorine, the chemical shift value also increases from iodine to fluorine if they are found as a substituent in an organic compound. I have taken one example named methyl substituted halides. The chemical shift values of methyl fluoride will be the maximum. It is 4.26, and methyl iodide will be the lowest. The value is 2.16. The reason is the electronegativity difference. What is the reason? What is the connection between the shielding or deshielding of protons with the electronegativity? In a molecule of methane, we have all the 4 hydrogens in an identical environment. So there is no question of electronegativity or electropositivity. There is no substituent. So the chemical shift value will be definitely lower than 2.16. But if you put one substituent, the electronegativity increases, iodine. Because of the electronegativity, the substituent is able to attract electrons towards it. See, in a molecule of methyl iodide, we have 3 carbon hydrogen bonds and 1 carbon iodide bond. Because of the electronegativity, the iodine attracts the electron towards it. So, the electron density in the 3 CH bonds will be displaced towards the iodine atom. As a result, the protons are present in a deshielded environment when you put a electronegative substituent in an organic molecule. So the protons of methyl iodide are experiencing a higher magnetic field when compared to methane. If you change the substituent from iodine to fluorine, as the electronegativity increases, the de-shielding effect is more. So the chemical shift values of the protons of methyl fluoride is the highest. It is around 4.26. So always you must remember, the chemical shift values of a proton increases with the electronegativity of the substituent. The reason is the electronegative compound produces maximum de-shielding around the protons in its vicinity. So as a result, the chemical shift value is higher for the protons when you have a electronegative substituent like fluorine. See, let us go to the next slide. As I told you, just like electronegativity, the electropositivity can also affect the shielding or de-shielding effect. One example we saw that tetramethylsilane. In tetramethylsilane, silicon is highly electropositive. So as a result, the electron density is displaced from silicon atom. So the protons of tetramethylsilane, 12 protons, they are experiencing a higher shielding effect. So as a result, the chemical shift value will be the lowest and it is assumed as 0. When compared to the organic molecule, the frequency of absorption will be the lowest for tetramethylsilane. So the frequency of absorption is assumed as 0 for the reference compound. Just like the silicon, which is electropositive, we have various organic compounds where the substituents, instead of having electronegativity, they are having electropositivity. They are having the positive charge over them. For example, you have the quaternary ammonium ions, tetramethyl ammonium chloride. What about the chemical shift values of such compounds? Tetramethyl ammonium, nitrogen is having a positive charge, it is in a quaternary state. As a result, what happens, the electropositivity here operates, the positive charge is over the heteroatom. So, the 4 methyl groups of tetramethyl ammonium compounds, quaternary ammonium compounds, they experience a lower magnetic field. Automatically, the chemical shift values will be lower. So as electronegativity increases, the chemical shift values increases. As electronegativity decreases, the chemical shift value decreases. The chemical shift value decreases with the decrease in electropositivity. It increases with the increase in electronegativity. I can give one more example. See, how about the carbocations? We have organolithium compounds, tetrabutyl lithium compounds, tertiary butyl lithium compounds, tri-tertiary butyl lithium compounds. So we have the cation over the carbon ions over the negative charge over the carbon. Similarly, we have cations. It is because of the heterolytic cleavage of carbon heteroatoms, carbon halogen atoms, tertiary butyl halides. If it undergoes a heterolytic cleavage, then the carbon will have a positive charge. It is your carbocations. So in such cases, electropositivity of that carbon will be more. So the protons will be experiencing a lesser magnetic field because of the shielding effect, higher shielding effect offered by the electropositive carbon. So the chemical shift value will be lower. Just opposite to the carbocations, we have carbanions. We have a negative charge. So the protons will experience a higher magnetic field, higher de-shielding effect. So the chemical shift value will be higher for the carbanions when compared to carbocations. See, just like the Electronegativity and electropositivity of substituents or atoms that is present in the molecules. We have the same substituent effect, but the substituents are not offering their effect through the intervening chemical bond. The substituents may offer the effect, namely shielding or deshielding effect through space. The geometry of the molecule favors the through space operation of the shielding or deshielding effect. This is felt in some tertiary substituted carbon compounds. For example, sterically hindered molecules, tertiary butyl or sterically hindered carbon compounds, ditertiary butyl substituted compounds, heavily substituted aromatic compounds, and cyclohexane system. In all these cases, because of the stereochemical complications, the shielding and deshielding effect of the substituents are operating through space. For example, we will see later on also. The axial and equatorial protons of cyclohexane exists in two conformations. We all know that. From the knowledge of stereochemistry, you can say cyclohexane molecule is able to exist in two conformations, the axial and equatorial conformations. The axial and equatorial hydrogens may change their positions if they undergo ring flipping. If you just rotate one of the carbon-carbon sigma bonds, then you will have the ring flipping. The axial protons become equatorial and equatorial protons become axial. So, because of the operation of through space, operation of shielding and deshielding effect through space, the axial and equatorial protons, they experience a different magnetic field, and this is called as your van der Waals shielding and deshielding effect. If the axial and equatorial protons experience a different deshielding effect, then they will show different chemical shift value. This is observed actually in various examples. Later on we will discuss the chemical shift values of the axial and equatorial protons in another instant also. So this effect is called as the van der Waals deshielding, that is operating in stereochemically complicated molecules. Now, let us move to the next important term. See, this is about the anisotropic effects. First of all, you must know the meaning of this word. What is meant by anisotropic effects? Actually, anisotropic, the root word is anisotropy. ANISOTROPY. If you recall the origin of this word, then one can say, if your knowledge in crystallography is very good, then you can say that anisotropy is a term from crystallography. Can you recall in what context the word anisotropy is used? When you make a comparison between the crystalline compounds and amorphous compounds in solid state, you will come across this term. What is meant by anisotropy in crystallography? It is a property exhibited by ionic compounds, crystalline solids, crystalline compounds, many of them are ionic. So the crystalline compounds are showing a property, namely anisotropy. The opposite term is isotropy, but it is shown by amorphous compounds. Anisotropy is not shown by amorphous compounds. That is the difference. Solids are two types. One is amorphous compounds, another one is crystalline compounds. Crystalline compounds are showing a property, namely, they are showing a very sharp melting point, very fixed, very sharp melting point. That is a property of crystalline compounds. Whereas amorphous compounds are not having a very sharp melting point. Crystalline compounds show very sharp melting point, very accurate melting point, and another property is anisotropy. That means the physical properties are depending on the direction of the crystalline material. For example, refraction of light, refractive index, that is a property that is different in crystalline compounds. It depends on the direction. The reason is the crystalline compounds are having a fixed arrangement, it is not uniform. So anisotropy here means a different arrangement. It is not uniform throughout. Isotropy means it is uniform. In amorphous compounds, the arrangement is uniform. So what is meant by anisotropic effects? Any effect is not felt uniformly. For example, in crystallographic compounds, the refraction of light is not experienced uniformly throughout the crystalline material. That is why the refractive index is depending on the direction. So it is an anisotropic effect. So anisotropic effect actually means that the property is not felt uniformly throughout a material. Organic compounds are not experiencing the magnetic field uniformly. There are some organic molecules, many organic molecules are not experiencing the applied magnetic field uniformly. The protons present in them, the protons present in different parts of the molecule are not experiencing the magnetic field applied uniformly. They differ. That is why their chemical shift values differ. And such an effect is called as the anisotropic effect. See, this anisotropic effect is beautifully discussed in organic spectroscopy by William Kemp. First, I take you to the table 3.3, where the approximate chemical shift values for the protons attached to anisotropic groups are discussed. We have some groups which are offering the anisotropic shielding as well as de-shielding effect in the organic molecules. So go to Organic Spectroscopy by William Kemp or any other spectroscopic book. All the spectroscopic books are beautifully dealing. I am using Organic Spectroscopy by William Kemp as a reference book. You can purchase a copy of William Kemp also for about some 600 or 700 rupees through online. So table 3.3, approximate chemical shift ranges for protons attached to the anisotropic groups. Let us see the structure of the anisotropic groups and the approximate chemical shift range in delta values. See, these are the various anisotropic groups. A carbonyl group, COH, carbonyl group in an aldehyde. So the carbonyl group is offering an anisotropic effect. Carbon-carbon double bond, a ethylenic group, a carbon-carbon double bond. A benzene ring has 3 carbon-carbon double bonds which are conjugated. So there is a circulation of pi electrons. In a molecule of a carbonyl group, carbon-oxygen double bond, you have a pi bond, carbon-oxygen pi bond. Carbon-carbon double bond, we have carbon-carbon pi bond. So the circulation of pi electron is offering a shielding or de-shielding effect when it is placed over a magnetic field. It is very clear. The circulation of pi electron and the direction of the circulation of pi electron in the organic molecule when it is placed over a applied magnetic field it offers a shielding and as well as a de-shielding effect to the protons attached to the remaining part of the organic molecule. See, a carbon-carbon triple bond that is also offering anisotropic shielding or de-shielding effect. See, if you look at the table, you can clearly say, in the case of a proton attached to a carbonyl group, that is aldehyde group, the chemical shift value is the maximum. The chemical shift value is found to be in the range, say, 9.5 to 10. What is the reason? If it is a ethylene molecule, carbon-carbon double bond, the proton attached to ethylene is found to be in the range, say, 4 to 8. What is the reason? In a molecule of benzene, we have 6 protons. All the 6 protons are present in the same environment in benzene. If it is substituted, then the environment of protons in benzene molecule is varying. If it is mono-substituted, we have 2 orthoprotons, 2 metaprotons and 1 paraproton. The chemical shift value delta is found to be in the range, say, 6 to 9 parts per million. And in a molecule of acetylene, you have carbon-carbon triple bond. There are 2 pi bonds. And the chemical shift value for the protons of acetylene is found to be in the range, say, 1.5 to 3.5. The value is lower than the protons of ethylene. What is the reason? Though ethylene has one carbon-carbon double bond lesser than acetylene, the chemical shift values of ethylenic protons are found to be higher. What is the reason? So it is all because of the difference in the circulation of pi electrons. Let us see how the pi electrons are circulating in these molecules one by one. So first let us see the circulation of pi electron in a molecule of ethylene. This diagram is given in William Kemp, page number 100. Let us see the pi electron circulation in a molecule of ethylene. See, alkenes, they have a carbon-carbon double bond. The carbon double bond is made out of a sigma bond and a pi bond. The pi bond is indicated with the donut-like structures or cashew nut-like structures, that is above the carbon-carbon double bond and below the carbon-carbon double bond. So it is how the pi electrons are circulating. When the pi electrons are circulating, they produce a secondary magnetic field when they are placed over a applied magnetic field H0 or B0. So B0 is the applied magnetic field. When you are applying a magnetic field of B0, see this molecule, namely ethylene, when it is left, the circulation of pi electrons produce a secondary magnetic field around the molecule of ethylene, around the carbon-carbon double bond. See, you can see how the pi electrons are circulating with the dotted lines I have indicated. See, the pi electrons are circulating from the bottom to the top of the ethylene molecule in the clockwise direction on one side, in the anti-clockwise direction on the right side. But whatever it may be, whether it is a clockwise direction or anti-clockwise direction, with reference to the applied magnetic field near the carbon-carbon double bond, the secondary magnetic field is opposing the applied magnetic field B0, and in the area where the protons are lying, the 2 protons HH, you can see the arrows which are turning upwards. See, the arrows are turning upwards around the protons of ethylene. That means the secondary magnetic field produced by the carbon-carbon double bond is aligning with the applied magnetic field B0. Now what happens, the proton in a molecule of ethylene experience a higher magnetic field. The magnetic field applied by you or applied by the machine is felt higher further by the protons in a molecule of ethylene or in a compound containing carbon-carbon double bond. Okay? So, as a result, what happens, the chemical shift value is higher. So, this is the figure that is given in William Kemp, page number 100. Induced anisotropic magnetic field. Induced anisotropic magnetic field induced anisotropic magnetic field. So, we just saw how the induced anisotropic magnetic field is producing a de-shielding effect around the protons, or the protons are experiencing a higher magnetic field. I have used. See? The magnetic field is paramagnetic. Okay? It is not opposing. If it is opposing, then it is a diamagnetic field. The arrows are up and down. Whereas the arrows are parallel. That means it is a paramagnetic state. So the protons are exhibiting a paramagnetic state. It is another word used for describing the de-shielding effect. So, the protons of a molecule of ethylene, they are experiencing a higher de-shielding effect, or they are experiencing a paramagnetic effect when they are placed over a magnetic field V0 due to the anisotropic magnetic field that is produced by the circulation of pi electrons in a molecule of ethylene. Let us see a few more examples. See, the same thing can be explained with the help of a geometrical structure also. How the circulation of pi electrons in a molecule of ethylene produces the shielding as well as de-shielding effect, or the diamagnetic and paramagnetic effect when it is placed over a applied magnetic field. See, imagine a carbon-carbon double bond. Choose the center point. The perpendicular axis is drawn through the center point. With reference to that axis, if you draw two cross lines at an angle of 36 degrees, okay, with reference to that axis, if you draw an angle of 36 degrees, then you get two cone-shaped structures. So, the two cone-shaped structures, the circle, that is indicating the anisotropic effect produced by the circulation of pi electrons in carbon-carbon double bond. So, the two circle-like structures in the cone-shaped structures that represent the totally de-shielded area, that represent the protons which are experiencing a paramagnetic effect when the molecule of ethylene is left over a magnetic field of B0. So if you have a proton which is lying in that area, it will show a higher chemical shift value. That is why the protons of ethylene are showing a chemical shift value which is higher than alkanes. We saw the values. The value is in the range, say, 4 to 8 parts per billion. Remember the data. You have to recall the data then and there. It will be a good practice for you. You have to by heart the data values. If you read the NMR spectroscopy repeatedly, or any kind of spectroscopy. It is a data-oriented subject. You should have a very good memory. How can you improve your memory? By repeatedly reading the subject. Write it. Have the writing practice. If you write a few times, then the data will enter into your mind. One time writing is better than 10 times reading. So, during your lesser time after studying the subject, try to reproduce the data in a paper. Take a pen and write the data. What is the chemical shift value of ethylenic proton, ordinary protons? How the electronegativity affects the chemical shift values of the protons in alkanes. I have given you the data. The data varies from iodine to fluorine. How it varies. Electropositivity of the substituent, how it affects, how the data is varying. So you can recall the data. If you recall the data, that will reinforce your memory and the data will be stored in your brain. And you can recall it at any time. Even if you sit in the interview after your studies, you can recall. So, if you draw two cone-shaped structures at the center point of ethylene molecule, then the spherical structures in the cone-shaped structure represent the area where the protons are experiencing a de-shielding effect when a molecule of ethylene is placed over a applied magnetic field of B0. What about the remaining part? If a proton lies in the remaining part, then it will experience a shielding effect or a diamagnetic effect. As a result, the chemical shift values will be lower. And we have one example for this one also. I will show you. See, in a molecule of alpha pinene, see, we have two methyl groups attached to one carbon. Such groups are called as gem dimethyl groups. And over the carbon-carbon double bond, you have a methyl group. If you look at the other structure, then you can say that the methyl group attached to the carbon-carbon double bond, since it is far away from the carbon-carbon double bond, its chemical shift value is around 1.63. The protons attached to a carbon of carbon-carbon double bond will be in the range, say, 4 to 8 parts per million. The protons of a methyl group attached to a carbon-carbon double bond show a chemical shift value of 1.63. Look at the two methyl groups which is far away from the carbon-carbon double bond. I have shown the tilted structure of alpha pinene. We have two methyl groups attached to the same carbon. The two methyl groups are in the same environment. Structurally, they are present in the same environment. So, they should produce a chemical shift value equally. But the two methyl groups, they show a different chemical shift value. For one methyl group, the chemical shift value is 0.75 parts per million. I have written it and I have indicated. For another methyl group, the chemical shift value is, say, 1.27. The 7 is edited. It is cut. It is 1.27. The chemical shift value is delta value is 1.27. What is the reason for the difference in the chemical shift values for the protons of gem dimethyl group in alpha pinene? So it is a olefin. The olefin has a gem dimethyl group. The gem dimethyl group must show the same chemical shift value for its protons, but the chemical shift values are differing. The reason is the carbon-carbon double bond, which is far away from the gem dimethyl group, though it is far away, it produces a secondary magnetic field due to the circulation of pi electrons when the molecule is placed over a magnetic field. As a result of the secondary magnetic field, we have zones or areas where shielding effect is offered and de-shielding effect is also offered. Here, the two methyl groups attached to the same carbon in alpha pinene are the gem dimethyl groups. One methyl group is lying in a shielded area and another methyl group is lying above a de-shielded area. As a result, the two methyl groups are experiencing different magnetic fields. The chemical shift values are different. So this is one example, one classic example for the shielding and de-shielding effect. Paramagnetic and diamagnetic effect that is operating due to the circulation of pi electrons in a molecule containing a carbon-carbon double bond. So this is one example. Based on these questions will be asked in the examination. In the next class we shall see the remaining part of anisotropic effect, that is from the carbonyl compound. With this I conclude today's lecture. In the next class we shall continue the anisotropic shielding and de-shielding effect that is operating due to the circulation of pi electrons in various compounds like ethylene or carbon-carbon double bonded compounds, carbonyl compounds, aromatic compounds, and acetylene compounds or compounds containing a carbon-carbon triple bond. So if I continue, it will totally come to 2 hours. With this I stop. In the next class we shall see the anisotropic effect. Thank you.